Okay, we're on YouTube. Welcome. Areg, please.
Okay. So, okay, thank you for a nice workshop, and I'm going to kind of continue what Yossi was telling about, but from a theorist perspective. Sorry, but some slides there will be some overlap with respect in terms of some slides. So yeah, I'm going to. So the talk is dissipative dynamics of an impurity in the presence of spin-orbit coupling, and I will explain how CISS effect is related to this. So, okay. So basically, since this is a general talk, I will again kind of give introduction to CISS, but it will be from a different perspective, and I will again describe what is the theoretical puzzle here. There are now different approaches to tackle this problem, and so I will discuss the different theoretical approaches, and finally speak about this, how we see the problem, some not full resolution, but some aspect of it to be resolved with, including dissipative bath. Okay, so yeah, so chirality, you probably already know, everyone. So it's just lack of inversion symmetry, basically left hand and right hand, and then mirror symmetry transforms one onto the other, and they cannot superimpose to each other. And there, as Yossi said, most of the molecules are chiral. So the current spin selectivity, so this effect was observed first in 1999 and then more conclusively in 2011. And so the effect is quite simple in terms of so how it is organized. So you just take chiral molecules, put them on gold substrate, then shine some light which emits electrons from the gold substrate, and then these electrons pass through the chiral molecule, this monolayer of chiral molecules, and then you observe what is the spin of the electrons on the other side, and you see that there is a polarized electron current on the other side, irrespective. So this is the results, irrespective of whether you use circularly polarized light or linearly polarized light. So with circularly polarized light, you get different spin to start with, emitted from the gold substrate, but with linearly polarized light, you get kind of both spins more or less equal. But in any case, in all cases, you get, after they pass through the chiral molecules, you see 60% spin polarization. And then the other effect which they observed is that when you increase the number of base pairs, which basically means making the molecules larger, longer, the polarization increases. There were this was the kind of the initial experiments. These were followed like other experiments, the one which also Yossi discussed. So you have a chiral molecule, you put a gold nanoparticle and then AFM tip, and then pass the current, and then with changing, and here you have also then, yeah, in the previous experiment, I would say that you don't have any magnetic field present in the system. In this case, you have a magnet, one of the contact is a magnet, then you flip this magnetization direction, and based on that, you see that the current is different depending of what is the chirality of your molecule, and that can be translated again to this polarization, spin polarization, and it's again, it can reach. Now especially with this experiment, they can reach into the 90 or 95% polarization. I'll mention that these experiments are done in room temperature. So it's, and then the experiment was kind of redone in by different groups using different molecules. So it's kind of shows that this effect is universal, and basically you have a current of electrons, you have chiral molecules, you get spin polarized current, and reversing spin or reversing the chirality is basically the same. So you can, they are interchangeable. So from the experimental perspective, I mean, there are different devices, as we just mentioned, and why we study CISS, then there is of course this one, which you already mentioned, is that you you can select enantiomers using these chiral molecules. They are pretty good spin filters, which is also quite important in terms of spintronics and spin electronics. And there is also the other issue that usually in organic molecules, spin lifetime is lifetime is quite large, and it's good to, from theoretical perspective, to understand what is the cause of this. So now, what are the puzzles of this effect? Because of course, yeah, chiral molecules, there's probably why we have this effect. I mean, the first thing you can say, of course, there's spin orbit coupling, but as I will show during my talk, it's not enough spin orbit coupling. At least if you had very strong spin orbit coupling, it would be enough, but that's not the case. Then people try to add additional components like collective effect, because usually experiments are done not by single molecule, you have many molecules on the substrate, on the surface. Then what is the, how surface affects the result? And also I will speak about dissipation. And then the other main question is also whether this is a transient effect, it's non-equilibrium, or it's a static effect. So these are kind of questions. So, okay, now theoretical approaches of CISS effect. So they kind of evolved in a way as the experiment evolved during the years. So the intuitive argument, which is quite simple, is you have a chiral, so you have a helical structure, helical potential, electron moves through it, so you can translate this helical potential into this effective spin orbit coupling because of that to some magnetic field, and then you have a Zeeman energy splitting between spin up and spin down, which causes this effect. The problem is the spin orbit coupling. If you usually these molecules are, it's just the carbon atoms, so the spin orbit coupling is not strong enough. So if you try to calculate this effective magnetic field, it's not enough to cause you this spin polarization, which is observed in the experiment. And this idea was there also for the later theoretical proposals, which I'm going to discuss. This problem was always there, that the spin orbit coupling is too small to account for the effect. So the first theoretical calculations were done based on the scattering approaches. So because, as I said, the first experiment was this electrons kind of emitted from the gold substrate and going through the chiral molecule. So this is standard scattering problem, which you can calculate using the scattering approach and use this Born approximation and do this series. And yeah, and then there's I'm just showing here result of one theoretical paper, and basically they see polarization, spin polarization, but it's small, and that's and then because to account for the experiment, they say, okay, the molecule, it's not a coherent process. You have incoherent molecules along, so you have several layers of incoherent scattering processes, so you can kind of add the things add up. That's why you get the overall large spin polarization. But even with this, they managed to get like 4% at most. Here, just to show one of my works, I also tried to work in this direction, but not. I was trying to address another question, whether, because up to this point, all the theory papers were considering the molecule to be as a helix, and I was trying to answer whether the helix is necessary or you need just the chirality. And for that, we kind of decided to consider kind of a quantum well structure where you have just the dipole moments, because that's also when, if you have anisotropic quantum well and dipole moments, it's enough. The system is again chiral, it's not helical, and then you can again introduce spin orbit coupling and do the same scattering problem. And I also see spin polarization, but here again, if I use kind of relativistic spin orbit coupling, it's way too small to see anything. And even if you try to kind of introduce the fact that molecules are kind of a medium where you have enhancement of spin orbit coupling similar to other solid state materials, but even with that, it's not, you cannot get the values. So here I'm artificially increasing the spin-orbit coupling to see some polarization. But at least I see the dynamics is, so polarization is more or less energy constant, energy independent, and then it increases with the length of the system. So that's kind of, it's a similar trend as in the experiment. Okay, now let's come to the next approach, which was again coming because of these transport measurements. And at the first people tried to do this transport calculation using 1D models of the molecule, some helix. So I heard a lot in this workshop about people trying to do 1D polarons. But the problem here is with if you try to do 1D for this case, you can't progress much, because the problem is the spin orbit coupling is, if you are in 1D, it's just the SU2 gauge field. So you can just gauge it out. So in effect, it doesn't produce any polarization. So just staying in 1D is not enough. So you need some more than 1D system. But there are even stricter conditions which were derived independent of the CISS during the years and some different people. And the fact is that if you have some medium and then you attach 2 leads, but which are just one terminal, and then just pass a current, as long as your medium doesn't break time reversal symmetry, you are not going to see any spin polarization. So this is kind of quite restrictive. So either you need to have more than one, each terminal should have more than channels, or you need to kind of break time reversal symmetry in your system. And to show one of this type of calculation so they took, you see, they took here just 1D helical structure, but as I said, because for 1D spin orbit coupling can be gauged out, they kind of have 2 types of popping. One, this is kind of tight binding calculation, so they have popping both like this and also between the different turns. And the fact, but as I said, even this is not enough, because you have here this issue, and they are considering these channels to be just have one channel attached to one lead attached to each end. So that's why they also needed to introduce some leakage to the system, which is done usually in this kind of systems is done by these particular leads, which you kind of add dephasing leads where the electron when travels to these leads, they are like artificial leads attached to each side. Electron goes there and then it loses its coherence. And with that, they managed to get polarization, but even the polarization which they see requires quite strong spin orbit coupling, which cannot be counted with the whatever is cannot be counted with the spin orbit coupling of the carbon atoms. So yeah, then the other aspect which was discussed was maybe the spin orbit coupling is small in the molecule, but it's because of the spin orbit coupling of the substrate, because original experiments were done with the gold, so gold has a strong spin orbit coupling. So there were a couple of papers on that they basically assumed that spin orbit coupling is of the substrate, and then you have a molecule which acts like, or only it's because it's a chiral structure, it selects different orbitals, and so your electron counts because of the spin orbit coupling, spin gets entangled with the orbital or angular momentum, and then your molecule filters specific angular momentum channels, which effectively also filter spin. And this approach works and gives quite a good result, but the problem is then the experiment was kind of repeated with the silver and other substrates which do not have strong spin orbit coupling, and the effect was still there. So, and that's why the now kind of consensus is that substrate has an effect, but it's not enough to account for the full CISS.
Just to be sure, what is the definition of P here? What is that? Is that the fraction of
It's basically current of spin up versus spin minus spin down divided over total current.
Okay, for the polarized inputs or not unpolarized inputs.
Unpolarized, yes.
Okay, excellent. Thank you.
Yeah. The other aspect is that as I said, usually on the substrate you don't have just single molecule, and usually have many molecules. Even the first experiment which I showed where they did this food called nanoparticle, usually under the nanoparticle you have tens or hundreds of molecules attached, and so it means that maybe it's a collective effect. And actually this is the first experiment which was done. It's in 1999. There they tried to kind of mix pure. So first they took the pure kind of pure chiral molecule structure, which is only one. Here it's left chiral molecules. Then they added 1% of the other one, and they saw that the effect disappears. So it shows that maybe this is a Manybody effect, but this was kind of the first experiment, so maybe it's not too reliable. But we kind of tried to build a theory on top of this, and we tried to understand how the scattering will work. If let's say we have we model here molecules just as magnets, zero range magnets. It's simple because we wanted to make the problem quite simple. So we have a lattice, 2D lattice of the magnets, and then we scatter spin unpolarized current on top of it, and we can actually solve it analytically. That's the good part of it. And then and we also considered when you have two layers of this stuff. Just I will describe why we considered this, but this is not related to CSS. So and then the result is what we see, that you can obviously, because now you have this lattice, you can tune into resonance effect, and because of this resonance, so here this A is the scattering length, so we consider non-spin polarized scattering length, and A1 is the spin polarized scattering length, a spin selective scattering length. So if we have just spin selective scattering length, we see some polarization reaching to 1 for some values of the no, see, okay, here it shouldn't be A1, I guess. But the problem is the polarization, the transmission is very small here. So in effect, what happens here at the intuitive level, you have kind of as I said, the resonance effect, and the system acts as a mirror for one spin polarization, and so it reflects back completely one spin polarization and passes only at the other one. I mean, so this was for A00, and these are when you have both A1 and A0. Yes, so here this B is the separation, the distance between these points. So so it controls in effect, it controls the density of molecules. So when you have both A1 and A0, what happens, you see again, at some point you see this resonance effect, and you see polarization going from -1 to 1. And this happens because basically for different relative distance between the molecules, you get one spin filtered and versus the other. So there is some effect, but as I said, this is very fine-tuned because you need to have a resonance. And so we to get also some useful device out of this, we also tried 2 layers, and with 2 layers you can actually get higher spin polarization for a range of values, and it's not picked only in one place, and that kind of gives you can get you can make a spin filter out of this, but this is a different story because then you need to use kind of you can use, for example, magnetic atoms and put them inside some semiconductor and create such a spin filter. So although, as I said, this is kind of a resonance effect and it needs fine tuning, there are actually some indications even in the for the last few years, there are some indications that Manybody plays a role. So this one is called sergeant and soldiers effect. So what they did here, they basically, so this is the circular decroying, which is observing with the optical measurements. This is the standard way to observe right and left circular. So you use right and left circular polarized light to observe what chirality of the molecules you have, and this is the CISS effect. So what they see, they start with the achiral system where your polarization is or slightly, yeah, it's almost zero. It's here, it's not zero. Here, it's zero. Then you start adding the fraction of the chiral molecules. In principle, the increase of the polarization should be linear, but as you see here, you observe this non-linear behavior, which means there is a non-linear enhancement of the effect, and this again shows that the Manybody effect is somehow important. The other indication is this thing that this was also seen in two experiments. One is Yossi's group, and the other is Ron Naman, I think. And they saw that when you change the temperature, you can actually flip. So you take let's say chiral molecules, then you flip, then you change the temperature, but your effect gets flipped. And in both cases, the papers claim that this is because by changing the temperature, you effectively change the structure of the molecule and go from right to left. But if we kind of try to argue also from our theory perspective, it's when you change the temperature, these molecules they can also, the separation between them can be changed because there is some reorganization going in the monolayer, and that can change the distance between the molecules. And as I showed, the distance affects, so maybe they basically tune into this regime of this transition point. And that's why they see this effect. So this is kind of some indications. Of course, these are not conclusive, but just to give you an idea. And okay, now we come to the main question, which was also asked in the Yossi's talk: does the molecule break time reversal symmetry? Related to this, there is this issue, which is also standing problem in the community. So when you observe, so when they do this current measurement, you change as I said, you change the magnetization. So the one blue is for magnet. So you have here the magnet, you change the magnetic direction from up and to down, and you see this kind of current voltage characteristic. The problem is that if you follow the Onsager relation, which is extremely general, it says that if you change the magnetization and magnetic field and change the direction of the current, you should have the same effect. Or there is also reciprocity theorem, which even doesn't require you to change the current direction. But this only works in linear regime. Of course, you can claim that here it's not linear regime, but you still need to follow this Onsager relation. And if you look here, this Onsager relation is violated because you flip the sign. On both sides you have only blue one being stronger, not the. So you just flip the magnetization, you flip the current, but you don't get this effect. You get the other one being stronger. And this of course, this is true if your molecule is not breaking time reversal symmetry. If it breaks time reversal symmetry, then you should also flip the sign of the molecule. You don't do here. You just change the sign of the magnetization of the ferromagnet. And so this is one indication that maybe molecule actually breaks time reversal symmetry. The other one, this is the one which already Yossi showed. So you attach molecules on the ferromagnet, and then you see because of the chiral molecules, you flip the direction of them, you magnetize the ferromagnet. And this other experiment, which also discussed by Yossi, when you have this MV centers, you can actually probe the time, and you see it lasts for 10 or 12 hours. So even if it's not static effect, it's non-equilibrium, but it's long-lived, extremely long-lived. And yeah, so this is, and there is another aspect which is there, is that when you somehow the molecule, then now I'm kind of trying to bring the indication of the path into the game, because so what they did in this experiment, they did measure the CISS effect with the hold voltage, which I will discuss also later. But basically what they did here, they damaged the DNA sites. So they have DNA molecules, then you damage them, and somehow the effect gets stronger. And the other effect, of course, which is also interesting, is here they do this, again, similar Hall measurements, and they see that spin polarization gets stronger with temperature. So this shows that somehow temperature and environment plays a role. And now I guess both our group and also other groups are starting to discuss the issue of the coupling to the bath. So yeah. So how we see that, we kind of assume that we think that because you have spin orbit coupling, so your spin gets locked with the momentum, and then you have a friction, or because coupling to the bath. So when let's say you attach the molecule to the substrate, you get some electrons into the molecule, and then this electrons, depending on the spin, move in the different direction of the molecule, and because of the friction, they get locked, and then you get this spatial separation of the electrons depending on their spin in different parts of the molecule. So yeah, and okay, for that we need to specify what is the bath. For us, the molecule acts as the bath of phonons, and that's the way we see the bath in the system. And yeah, so right now we have the theory, which is a phenomenological theory. So it's a Schrödinger equation where we add the dissipation. Of course, there are more elaborate ways, and I will come to that, how to use also the how to account for the dissipation. But here we did just a simple Schrödinger equation where we add this potential, which is a nonlinear potential. It depends on expectation value of the momentum and expectation value of the position. So with this nonlinear potential, you can account for the dissipation. And when you solve this with this equation, you actually see that this momentum, average value of the momentum, is determined by the spin orbit coupling and the spin. And that's why, which is basically related to this spin momentum locking. So this means that your this potential of dissipation is different whether you have spin up or spin down. And so effectively what you get is you start with the system where you have electrons sitting in the center of the molecule, and they are spin up and spin down. And then after some time, because of this potential, they get separated, and you get different spin of different electrons with different spin being on the other different sides of the molecule. So you get spin separation. And yeah, we kind of calculated the expectation value of the position, and we see that it basically changes it either positive or negative depending on the spin. And the good thing is, which is very important here, we kind of get that it depends not on spin orbit coupling parameter, but it depends on the spin orbit coupling times the dissipation parameter. So basically, in your system, you can have this also kind of can explain that you have a small spin orbit coupling, but having strong dissipation, which we know it's true because in the molecules, the mobilities are extremely small. And this shows that you have a strong dissipation in the system. So, and that kind of can account for the strong effect, although your spin orbit coupling is small. And yeah. And we also apply this theory to some specific molecule, which is in this particular case was helicin, and we see kind of we took the mobility of the helicin. From that, we calculated this dissipation parameter, and here this PZ is essentially the separation of the spin up and spin down divided by the turns of the helix, and we kind of see that we get almost the electrons with different spins separated completely in different sides of the molecule. Yeah, this also kind of, there's experimental indications similar to this. One is this whole device measurement. So what they do in this whole device measurement, they put molecules on a 2-dimensional electron gas and then apply just the electric field to polarize these electrons, and then they see whole current. So there is no magnetic field in the system. It's just an electric field, but they see whole current. And they experimentally they say that charge distribution is accompanied by the spin polarization, and something similar we see in our case. Although in our case there's no need for this additional type of electric field. We claim that it can come just because of the electrons travel from the substrate to the molecule, and because of dissipation you achieve this regime. Of course, if you apply electric field, the effect will be stronger. But yeah, and yeah, the other thing which also Yossi mentioned is this the fact that when molecules put on the superconductor, they show this zero bias peak. So there is some change of the order parameter. This usually happens when you have a high density of molecules and you have 2 temperatures here. So zero bias peak disappears earlier than the TC. And for the small density of molecules, you start seeing shivalike states, and this cannot. So this cannot be even though the change of the order parameter can be counted by the spin orbit coupling, but the shivalike states, there's no way to count them with just spin orbit coupling. You again need to have some magnetization in the system, and this again proves that you need to have a time reversal symmetry breaking in some form. And yeah, this is actually this theory which is presented here is done assuming that you have a magnets sitting on the superconductor. So this theory is already assumed that there is a time reversal symmetry breaking. And with our theory, we can of course account for that, because as I said, electrons go in different parts of the molecule, and you basically on the position where your molecule gets attached to the substrate, you have electrons with specific spin, so you have a magnetic moment, and that's why you can get a Shiba state. And then here we show that the Shiba state depends on the coupling strength between molecule and the substrate, which is also known effect, and you can essentially control the position of the Shiba states. Now, as I said, this is not the end of the story, because the model was phenomenological. It requires, if you want to account for the dissipation and coupling to the bath, you need to consider more elaborate models. The one which we are currently working on is the caldera leggett model. So we kind of started the caldera leggett model in 2D system with spin orbit coupling. So in caldera leggett, you get dissipation and you get also decoherence. But when you derive the new caldera leggett model, you actually get this new term when you add the spin orbit coupling. And the thing is that now the problem is with this, when we try to calculate the spin polarization, this new additional term kind of cancels the effect of what we envisioned in this phenomenological model. And that's why when we calculate the polarization, we see it's a long-lived polarization, but it's first of all doesn't get enhanced with dissipation. Dissipation is actually, we don't get alpha times gamma, but dissipation actually works against it, and it makes it smaller. And also, yeah, for longer times, your polarization goes to 0. Now we are kind of trying to understand what is the cause of this. Of course, the caldera leggett model has number of approximations in it, and it's not the end of the story. It's semi-classical model. So we are kind of trying to understand what else, how to make the system more kind of similar to what we had in the phenomenological model. So we are discussing the issue of whether quasi-1D system can work. There's also beyond caldera leggett models you can, and then you can also consider that spin-orbit coupling does not have to be spatially homogeneous in your molecule, because the part which is attached to the substrate most likely will have stronger spin-orbit coupling, and so you will have some special profile of the spin-orbit coupling in the molecule. So this idea of Polaran model, because basically this is a Polaran model of the, because you have electron tunneling inside the pad with spin-orbit coupling, is now kind of, it's getting more attention. There are already 3 papers which more or less do similar calculation, and some of them see, so here they do again at the pad, and they see because of the pad coupling the polarization gets enhanced compared to here. And yeah, and this is the Franson paper. This is this one. It also discusses kind of coupling to the vibrations and or phonons, and they also see more or less the same effect, that the effect gets enhanced if you have a coupling to the pad. And I would like also to mention that this question is also getting attention on a general basis, not related to CISS effect. Can you break Cramers degeneracy if you couple to the pad which doesn't have spin structure? If the pad has a spin structure, then it's kind of trivial that you can get this kind of stuff. But what if you have an electron with a different spin, and then it's connect to the pad, which more or less, and this coupling is time reversal invariant. The coupling doesn't break time reversal symmetry. Of course, the coupling to the pad by itself breaks time reversal symmetry if you consider only your system, your electron, but the coupling doesn't break the symmetry. So there is this recent paper by McGinley and Cooper where they show that actually if you consider linear expansion of the coupling, you can't break this symmetry. So spin up and spin down are still degenerate. But if you go one order higher, you start. So this linear coupling corresponds to Markovian dynamics, which you get standard Lagrangian form density matrix equation. But if you consider higher order terms, this quadratic term, you can actually, which accounts for the scattering from this ground state of spin up and spin down to higher state and back, you can essentially introduce decoherence in your system, and which in some sense means that you can break Cramers degeneracy. And there are other papers discussing this, but there's also this last paper which claims that if you do higher order, even higher orders, eventually this effect will disappear if you consider static long time regime, but you will see some separate Cramers degeneracy breaking, but it will be transient effect. So this is still highly debated issue, and it is discussed in these different papers. Yeah. So, and finally, I just thank my collaborators in IST. So I'm from IST Austria. My collaborators are Artem Volosnev, Mikhail Nemeshko, Alberto Capolaro, and from Hebrew University, and Alpern, Yossi, and Odette Milo. And thank you.
Would you be able to comment on the dependence of the polarization on the bias or the current? How does this effect depends on your system being away from the equilibrium?
You mean no?
Well, not in DC. Okay, so not in the linear. So you have polarization, which you plot everywhere, but that I suppose is in the linear response regime. So if you
this is also debated. I guess they are saying, so according to this, what I said here in this reciprocity theorem, in linear regime you shouldn't have the polarization. It's not true if the molecule breaks time reversal symmetry, but
Yes.
it looks like, according to experimentalists, I'm not sure, but according to experimentalists, they are reaching to nonlinear regime. So they are not, the system is not linear.
We believe it's nonlinear regime
Oh.
because you put huge voltages.
Right. So okay, that's illuminating. But then the figures for the polarization that you quoted in the previous, in the early pages of your talk,
Okay.
those
Yeah.
those then describe
Nonlinear again.
nonlinear. Okay.
It's always nonlinear. Yeah.
Right. Okay. All right. That's very interesting. Okay. Thank you.
Alright.
Yeah.
So what material do you suggest for us to check if you want to see between all the last series that you talked about? Want to differentiate? Thanks. If you want to differentiate between the last series you talk about, so what material should we check to see?
So you mean?
Not this one. This one I know, but you talk about going beyond the friction, the simple polar. How do we differentiate between the different polaron pictures? Temperature dependence or what?
Yeah, I mean, I guess the temperature dependence will be slightly different. Well, right now, as I said, we still don't have a theory, because if you, in our phenomenological theory, temperature dependence doesn't come into play. It is somehow hidden in this dissipation parameter, but now we are trying to do this caldera leggett model where this beta parameter is essentially 1/T. So temperature here enters explicitly, but right now we still don't have a working model in this. We are trying to get this to work, and if we get this work, this will have some temperature dependence, and it will be probably different compared to what was observed by Franz, because now there is this paper on temperature dependence. Yes, where is that?
From Jonas.
Yes, from Jonas, and it will be good for us to also check with our calculation. To see whether we can get something similar as a temperature dependence. So this is one thing which can help in this direction. The other one, what else you can do with this? You can also, it's the molecules.
We can change the density of molecules, of course.
But that's more like a Manybody effect, how the Manybody effect affects.
Because if you don't have a difference between the theories, if you don't have an experimental prediction, it will be hard to differentiate.
Yes, I see. Well, the standard with temperature, but what else can you do to? The other one, as you saw, this effect of kind of introducing some damages into DNA. This is also, I think this is also in some way related to this. And in some way, if you, for example, if you can somehow modify your molecules, even if they are not you don't modify the chiral structure, but introduce new modes of new phononic modes, which will come because introducing different atoms into the system. So you can kind of,
this could be done because you can add a vibration.
Yes, and that will also, if that enhances the effect, this is another measure of that this is coming from dissipation and the bad coupling. And that's
Okay, thanks.
Yeah.
Do we have anybody questions? Okay. Thanks.
Thank you.
Yeah.